distribution or a discrete distribution. Some of the properties we simply said that each individual probability should be between 0 and 1. Sum of all probabilities should be equal to 1. But out of that, if there are some common scenarios, see, why do we typically use these probability distributions? One, to model our business processes. Right? How does, let's say I want to do some kind of a modeling for number of claims that can occur during a particular period. During 1 year, what is the chance of getting 20 claims? What is the chance of getting 40 claims? I want to model something like that. Right? So anything where I want to model something related to the discrete items. What are these discrete items? Countable kind of items. Number of claims, number of successes, right? Number of something. Whenever we are trying to model number of something, we are talking about discrete probability distribution. So various kinds of models that are available for modeling number of something, and any kind of these models for whatever we are going to discuss now, there are three important things that we need to understand. One, in which context I can use this kind of a model, right? For what business purpose I can use this kind of a model. How do I find out the probabilities using this model? And finally, I am also interested in finding out what are the characteristics of this particular model. Characteristics are nothing but the mean, the variance, something like that. Right? For each of the model, how do I identify whether it is a form of uniform distribution or a binomial distribution or a Poisson distribution? What makes me identify that it is belonging to that category of distribution? Once I know that it is a particular type of distribution, how do I identify the probabilities of that particular occurrence of one event or two events or whatever it is, number of something, and what is the average of it, what is the variance and standard deviation, mean and variance and the standard deviation associated with them, right? So we'll start off with the uniform distribution, the first of them. Simple. See, formulas wise you need not memorize, because most of these formulas are given in the tables. So the intention of this exercise should not be memorizing of the formulas, but understand where I should use these kind of distribution, for what kind of a purpose I can use this distribution, or from a business example which he has given, how can I convert it into this distribution, right? Those are some of the aspects that we need to understand. So the first of those distributions is the uniform distribution, where all the items have equal chance of occurring. All the outcomes which we are talking of, if they have equal chance of occurring, let's say for throwing a dice, right? We can get 1, 2, 3, 4, 5, 6, and all of them have an equal chance. It's a fair dice. If it is a biased dice, where some edge is broken or something, where there are some high chances of getting some number compared to the other number, then it does not follow a uniform distribution. But if it is a fair dice, or where people say equal chance for everyone, right? Whenever I say that there is an equal chance of occurring, I can simply take the probability of occurrence of each of them is nothing but 1 by 6, How did I get this 1 by 6? Because there are 6 possible outcomes here. There are 6 possible outcomes. So each outcome has a chance of 1 by 6. So whenever I create a distribution of this form, whenever I see any example where the distribution is of this kind of a form, we categorize it as a uniform distribution. Now, in our earlier chapter, what we have simply said is this is a discrete distribution. We did not call it as uniform or whatever. We said this is a discrete distribution. So for every distribution, what did we do in that chapter? We found out what is the mean of that. Mean, how do I find out the value into the corresponding probabilities and then add up? And variance, we have found out expectation of x squared minus expectation of x whole squared. So for this I can find out the variance. Now what they say is, if at all I know this distribution is following some kind of a pattern, the mean and the variance, probably you don't need to sit and calculate doing this entire exercise. They are outrightly known. They are derived. What you are doing is the same. Let's say in this exercise, if I want the mean, 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6, which actually comes out to 21 by 6 or 3.5. What he says is, don't do that entire part. If you know that it is a uniform distribution, take the mean as n plus 1 by 2, where n is your total number of variables. So 6 variables are there, right? 6 outcomes are there. So you directly say that the mean is 3.5. You are not even calculating it. Well, if you calculate also, you will get the same thing, right? The same way variance. Now if I have to calculate the variance, I have to do expectation of, the typical way is, variance is expectation of x squared minus expectation of x whole squared. This is the formula which we have looked at earlier, right? Expectation of x we got as 3.5. So expectation of x squared we will get by substituting x squared in place of x for the first row, and then multiplying it with the corresponding probabilities. And after I do that, whatever I am getting is the variance. Now it says, if it follows a uniform distribution, you don't need to do that entire aspect. The variance is directly coming out as n squared minus 1 by 12. N is 6 here, 36 minus 135 by 12 is the variance. If I know that the particular distribution is a uniform distribution, then I can very well say that the probability of occurrence of each of them is 1 by n. The mean of it is n plus 1 by 2. And the variance of it is n squared minus 1 by 12. Right? Of course, no point in memorizing, but so you need to understand which scenario I have to use it. If all of them have equal chance of occurring, I can use this uniform distribution. Now, the next one is called as a Bernoulli distribution. See, in the uniform distribution, we talked about n number of outcomes, right? And all of them have equal chance. Now, the Bernoulli distribution says there are only 2 outcomes. Even if there are 6, you create them as 2. Success, failure. What you want, you call as success. Again, success is not an English word called success. Here it is what you want. What you want to observe is called as success. What you don't want is called as a failure. Let's say when I am throwing a dice, right? When I am throwing a dice, if I want 6, so 6 is a success. Other than 6 is a failure, which means there are only 2 outcomes for me, right? Of course, in isolation, we don't look at too much into the Bernoulli. The Bernoulli actually will be used to a large extent in many other distributions. In the binomial distribution, we'll use this mechanism called Bernoulli. In geometric distribution, the next which we are going to discuss, there also we use this Bernoulli. So Bernoulli is just a base for us to understand. We are not talking about outcomes here. We are trying to group the outcomes into only two outcomes called success and failure. Right? Only two. And so the probability of success is P, then the probability of failure will be 1 by P, 1 minus P. Right? And so the simple way, if you want the probability of success or a failure, you can simply take it as probability. Let's say if I want probability of x equal to 1, which means it's a success. I want the probability of success. I can write it as P of P power 1 into 1 minus P to the power 0, which means the probability of success is P. And when I say probability of failure x equal to 0, you put P power 0 into 1 minus P to the power 1, which is nothing but 1 minus P. So, simple way to understand Bernoulli, it is not a big thing to understand. All I need to find out is probability of success and probability of failure. Now, simple logic is, if at all if I am throwing a dice and I am planning to observe a number greater than 4. Number greater than 4 is a success. So, 5 and 6 are becoming successes. 1, 2, 3, 4 are becoming failures. So, the probability of success P is 2 by 6